How can a blurry image of a star help us understand more about their orbiting exoplanets than a clear, sharp image? It seems counterintuitive, but that's exactly what CHEOPS, or the Characterising ExoPlanet Satellite, is doing. CHEOPS is a space telescope launched by the European Space Agency in December of last year, with a mission to hunt down the most Earth-like exoplanets, which, as you can probably imagine considering the distances involved, is not an easy feat.
I'm Alex McColgan and you're listening to the Astrum podcast. And in this episode we will talk about the very promising ESA mission, CHEOPS.
CHEOPS is a joint effort with ESA and the Swiss Space Office, which is fitting as it was Swiss astronomers who discovered the first exoplanet back in 1995. It's hard to believe, given that we now have confirmed the existence of thousands of exoplanets, but it was only 25 years ago when we discovered the first one, so we are still in the early days of this astronomical field. The planet they discovered is now called 51 Pegasi b, or Dimidium, a gas giant around 50 light-years away in the constellation Pegasus. It is now considered the prototype for what has come to be known as hot Jupiters. These planets are similar in size to our gas giant neighbour, but orbit their planet star very tightly, some with orbital periods of 10 days or less. This means they are extremely hot due to their close proximity to their sun. The reason exoplanets are only just being discovered is because they are exceptionally difficult to observe, as they are hidden by the brightness of their stars. That's why we have to really think outside the box if we want to detect them. If you use a regular telescope to look at stars that are known to have exoplanets orbiting them, you'll only see the shine of the star, as its brightness compared to any close orbiting exoplanet is overwhelming. You can't even directly see exoplanets around the closest star system to us, Alpha Centauri, which is only 4 light-years away from us. If that is our closest neighbour, and directly observing through a regular telescope won't work, imagine trying to observe exoplanets tens to hundreds of light-years away. So how did those astronomers discover Dimidium? Well, hot Jupiters are often the easiest types to discover, if something like that can really be considered easy. Because they have a strong gravity and are close enough to their parent star, they both orbit each other around a centre of mass that makes the star appear like it's wobbling. Depending on the mass of the bodies, the centre of mass can be within the parent object, or with objects of a similar mass, it could simply be a point in space. Wherever the centre of mass is located is known as the barycenter. One of the most extreme examples in our solar system is Pluto and Charon, which orbit around a point above Pluto's surface. In regards to Dimidium, astronomers could detect shifts in the distant star's light and confirm the presence of a large exoplanet because it's causing the star to wobble. This method of detection is called the radial velocity method, or Doppler spectroscopy. The discovery of Dimidium, made by the Elodie spectrograph in France, won the astronomers a Nobel Prize, and it was considered a major breakthrough for European astronomy. Since then, there have been many new exoplanet discoveries, and we know now that the galaxy is teeming with planets. This is where the CHEOPS mission comes in. It is already in orbit and sending back more than 1 gigabyte of data every day. CHEOPS orbits in what is called a heliosynchronous orbit, 700 kilometers up around Earth. In other words, CHEOPS is in a dawn-dusk polar orbit. That means that it travels around Earth along the twilight terminator line, with the sun powering up its solar panels on its back. Meanwhile, its gaze peers deep into space, protected from sunlight interference. CHEOPS mission allows the telescope to study the smallest exoplanets we know, called super-Earths. They can be as small as our planet, but can also be as big as Neptune. The goal of Cheops is not to find new exoplanets, but to examine ones we already know about, to determine what they are made of and how they are formed. And that is very exciting, because it has the capabilities of discovering potentially habitable worlds. Planets that might have a similar size, orbit, and composition to our home. Cheops is much smaller than Hubble. It's only 1.5 meters across and uses a 32 centimeter mirror. However, it can see exactly what the designers had hoped for.
If you were to see those first images though, you might notice something peculiar. All the stars captured in them are blurry, with no exoplanets visible. Now, this isn't a design flaw. Cheops is working as intended. The reason for the blurry images has something to do with the second method of exoplanet discovery, namely transit photometry.
One of Cheops' key instruments is a very advanced photometer that can detect the tiniest amount of light variations on distant stars. If an exoplanet's orbit is aligned with us, it will transit the parent star so that it covers some of the star's disk from our perspective, in a similar fashion to a tiny eclipse. And that's what Cheops does. It monitors the amount of light it receives from a specific star and then detects light variations from when a planet crosses in front of its disk to see how much dimmer it gets. The reason the Cheops image is blurry is so that light from the star hits more of the camera sensor, increasing the number of pixels that get hit by the star's light. Through this, astronomers don't need to see the exoplanet itself, but this increased resolution allows astronomers to accurately record and study the star's light spectra itself, as well as any changes that take place from the exoplanet's transit. As you can guess, the bigger the planet, the more light it will obscure, and the easier it will be to notice a dip in light intensity. For small planets, however, this process is much more difficult to measure. And that's why Cheops is so important, as its advanced instruments and blurry images allow astronomers to better define the transits of those smaller, more Earth-like planets. Additionally, Cheops can measure a planet's phase curve, or how much light it reflects from its sun. When a planet is in front of the star, it will block light, but as it orbits around to the sides, it will reflect light back to us, which makes the star appear a little brighter from our perspective. Here, Cheops' photometer comes in handy again, this time to measure the increment in light variation. By comparing it to the light we receive when the planet is behind the star, when it's not interfering with the star's brightness, scientists should be able to isolate the spectrum of the light reflected by the planet. With that, they will be able to know the composition of the planet's atmosphere. And since they are investigating only the most promising planets, they can take multiple readings for a more defined measurement. But why does Cheops have to be in space? Can't we do all these readings from Earth? Well, just like the James Webb Telescope, telescopes here on Earth face two main hurdles. The first one is that we have night and day. That's a large section of a 24-hour period when no observations can take place. We might miss an important transit during that time. But even at night, the light a telescope receives is distorted as it travels through Earth's atmosphere. Photons hit several particles in different layers of the air, making the light flicker and wobble. Even if there are several methods to counter that, the readings would never be as accurate as they would be in space. That's why Cheops was launched into a sun-synchronous orbit. As I mentioned before, it will ride the terminator line of Earth. This not only allows it to receive constant light on its back for the solar panels to generate power, but it also means it can take a look at stars 24/7 without sunlight interfering with its readings. So, as you can see, with all the data Cheops will hopefully collect, it may just be a matter of time until we can confirm the existence of another planet like Earth. A planet with similar mass and temperature, with the presence of water and oxygen in its atmosphere. All the right conditions that harbored life here.
Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on the Characterising ExoPlanet Satellite. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.
you.